Well, hello everyone. Mr. Minnick's my name. Math is my game. Today, we will be looking at the first half of Chapter 4, Section 8. The title is very misleading. The title is very confounding. The title is simply complex numbers, which, if you understood exactly what complex numbers were, you would understand why I believe that that's a confounding or misleading title. So you probably are thinking, what are complex numbers? So we'll go down memory lane for a minute, and it shouldn't take that long. So when you were 4, you learned in preschool to count. That's one of the things before you can go to kindergarten, you have to be able to count, right? And I love listening to little children count. 1, 2, 3. All right? So we studied those numbers at the beginning of the year, the first week of class, perhaps. Second day of class. Anybody remember what those were called? They are rational, but they were called, they're not whole numbers. Well, they're not whole. They are real, but there's a most specific type of number. 1, 2, 3. What are we doing there? We're counting, right? To the counting numbers, otherwise known as the natural numbers, okay? And then all of a sudden we said, well, let's drink the best milk you could possibly drink. And then those are the whole numbers. So all natural numbers are whole, with the exception of 0. The wholes and the naturals are the same. And then we looked at these ones, -1 and 0 and 1. And those were the integers, right? And my boxes are really going crazy. That's okay. It's all good. And then we had some fractions, right? And then we hated math. From then on, we said, nope, we suck at math. We're no good. Math is evil. And then you learned about some other numbers, like the square root of 2 or pi. And those are irrational. Good. You cannot write pi as the ratio of 2 integers. It can't be done. Pi is the ratio of a circle's circumference to its diameter, but you can't write it as 2 integers. So what happened then is there was this bax. A big bax. And we said, you know what? Every single number that's in that bax is this kind of number. And people always ask me, Mr. Minnick, why do you use that weird symbol? Well, because it's the symbol for the set of real numbers. Google it if you don't believe me. It's a fancy R. It looks like the Rawlings R, doesn't it? Okay? So that's why I use it, because it's what you're supposed to do. Well, along came something else. Along came some kind of number that's not real. Yeah. Imaginary numbers. Okay? Imaginary numbers are not real. But math people said, wait a minute. Rational numbers belonged somewhere. Irrational numbers belonged somewhere. What about the imaginary numbers? Them and the real numbers have to belong somewhere. So where do they belong? Well, here we go again with another bax. We need a bigger bax. I'll make it blue this time. So all those belong to, guess what? The complex. So it's kind of weird when we say complex. What we're really saying is there's probably going to be some imaginary numbers. Okay. But by design, every single real number is complex. Every single irrational number is complex. But the implication, when you hear the word complex, you should assume, they're probably talking about imaginary numbers being possible. Okay. Any questions so far? I'd like to say bless you to anybody that just sneezed. Example number 1. Let's try to solve x squared plus 1 equals 0. Now, we've been going down memory lane today. Not Penny Lane. I think that was a Beatles song. Anybody remember what the fundamental theorem of algebra says to us, what it tells us about equations? Say what? You can solve them. It says equations have solutions. An equation has a solution. What's it say about quadratic equations? We notice the exponent in this particular equation is 2. What's it say about quadratic equations? Yeah, it says the number of the whatever the exponent is, that's how many solutions it is. So the quadratic equation is going to have 2 solutions. So bearing that in mind, let's go ahead and try to solve this equation and see what happens. If you were in 9th grade, I know what would happen. You'd just walk away. Drop the mic and walk away. You'd say you can't do it, and you'd be right. But this isn't 9th grade. This isn't 9th grade. So let's try to solve this equation. What's the first thing you'd do? We're trying to solve the equation and get x all by itself. What do we do first? Minus the 1. So then that's going to leave us with x to the squared equals, if we subtract 1 from both sides, these cancel, and on the other side I get 0 minus 1 is minus 1, right? Now, we've seen how to solve equations like this. We want to get x by itself, not x squared. We want to get x by itself. So what do we do next? Take the square root. Good. So we take the square root of the left side, and when we square root something squared, that just leaves behind the radicand. So that leaves us with just x, right? Yeah. Anytime you take a square root when solving a quadratic, there's a certain character that we have to introduce, right? What character do we need so that we get 2 solutions? Plus or minus. We need a plus or minus. And so let's see what happens. Oh, TI-83, you're my most trustworthy calculator. You've never, ever let me down. You've never, ever, ever let me down. So would you please take the square root, I said take the square root of -1 for me. The square root of -1 is not real. And so that's why in varsity math we study imaginary numbers, right? Because the fundamental theorem of algebra says we got to have a solution. Its corollary says we got to have 2 solutions. So perhaps we can get our calculator to cooperate with us by going m to the isode. And do you see what we're going to do here? Do you see toward the bottom? Oh, so let's try that again. The square root of -1 is I. It's plus or minus I. It's the imaginary number, and we're going to say a lot about ion today. Okay? It's so weird. We're going to talk about I, not me. We're going to talk about I, not you. We're going to talk about I. I is a number. No, you are not. I is, though. So you might say to yourself, but wait a minute, that can't possibly satisfy that equation. What happens if I square I? There's no way that I squared is supposed to equal -1, right? There's no way that's true. I went ahead and stored I into my calculator as x. So x squared, this is supposed to equal -1, and it does. What about -I? There's no way that if I square that's going to equal -1, is there? Well, yeah, it does. It's true. So we need to talk about some things. Let's slow our roll a little bit. Let's look at standard form of a complex number first of all. Standard form of a complex number. And we're going to juxtapose that with standard form of an imaginary number, and they're almost the same thing. We're going to compare that to standard form of an imaginary number, And I'll be frank with you, even though my name's not Frank. They're the same thing. This is A plus BI, and this too is A plus BI. But what's the difference? Well, for complex numbers, it's true for any real number, A and B. A and B can be anything they want to be. For an imaginary number, it's true for any real number, A and B is not allowed to equal 0. There's the difference right there. That's it. B is not allowed to equal 0. That form, we're going to come back to that, but hopefully that kind of sheds some light on the calculator when we set it up, how we went from real to that other form. How are we feeling today so far? All right? Anybody have any questions? Okay, let's go to example 2. Let's try to solve 2x squared plus 4 equals 0. I had a teacher in 6th grade. I hope she doesn't watch the playback. She might not even be alive anymore. She might not be alive, seriously, but I'm not going to say her name to protect her anonymity. But this was back in the 80s, long time ago. Now, anybody familiar with prosthetics? They've come a long way since then. She was rumored to have prosthetic lady parts made out of, well, back then they didn't have the synthetic silicones and whatnot that they have nowadays. There's a point to why I'm telling you this, okay? You'll never forget it if you listen. If you stay off your cell phones, stay off of Twitter and Facebook and whatever you're on, and you listen, you'll never forget how to solve this equation. I guarantee you. Okay. So anyway, she stood about 4'11". She wore her hair like Marge Simpson in a beehive, so she was actually like 5'8" with her beehive, and she waddled when she walked. And her lady parts that were supposedly, they were made out of wood. That's what they said. I don't know if they were or not. Okay, but that's what they said. The kids really picked on her a lot, really a lot. But anyway, I don't know when it happened or how it happened, but I had an uncle who, when he was 12, he played with some blasting caps and lost one of his eyes. So he had a prosthetic eye or a glass eye. This woman did too. Okay, she had a glass eye, a prosthetic eye. Yeah, we'll come back to that. So let's go ahead and let's try to solve this equation. Let's try to solve this equation. We're trying to get x all by itself. So what's the first thing we should do? Subtract 4. So after subtracting 4, we're left with 2x to the squared equals -4. And remember, we're trying to get x by itself. Before we can get x by itself, we probably ought to get x squared by itself. So next we're going to go ahead and divide by 2. So that leaves x to the squared equals -2, right? Now, we're going to take the square root. So we take the square root, that's going to leave x. We take the square root, solving a quadratic, we're going to have to put in a plus or minus, right? Now, I don't know if you've ever seen someone really excited or not. I mean, somebody's super excited. But what happens when you get excited? Your mouth opens wide and your eyes open wide. I don't know if you know this or not, but an eyeball is about the size of a handball. It really is. With a glass eye, what they do is they take approximately 1/3 of the surface of a sphere and then 1 centimeter deep, and that's what they make that prosthetic eye out of, and it just kind of sits in the socket. It's not a whole entire eyeball. So this woman was teaching one day and got so excited and her eye popped out of her head. Now, there is a reason I tell you this. Let's think about simplifying radicals for a minute, okay? Off to the side over here, we've got the square root of -2, right? Everybody with me? Okay. So we always have some little magic trick in math. So we could write the square root of -2 as the square root of -1 times 2. Is that fair enough? Does everybody agree that -2 equals -1 times 2? Does everybody remember the product property that says that we can now split these radicals apart? Just a minute ago, what did we say that the square root of -1 was equal to? It was equal to I, right? So the square root of -1 then is going to become I, and the square root of 2 is going to remain the square root of 2. So what happens in this particular problem is an I pops out. And that's it. And that's it. Anytime we simplify a square root with a negative in it, an I pops out, the square root under the negative under the square root goes away. Right? Anytime we simplify a square root of a negative number, what happens is when we simplify that, to make that negative under the square root go away, we just pop an I out. And then the radicand becomes stays the radicand. Yeah, question. Oh, we're going to look at a bunch of them. We're going to look at a bunch of them, yeah. Radical 1 is just 1, and it's not very exciting. And we want exciting things to happen. We want I's to pop out. Okay? So a couple things. In case you missed this, the square root of -1 is the imaginary unit, I. That's the definition of it. The square root of -1 is called the imaginary unit I. And I'm going to go on to say this. I'm going to say powers of I are cyclical, and we'll come back to that. We'll come back to that. But powers of I are cyclical, and we'll look at that in a few minutes. But the square root of -1 is the imaginary unit I. So we had a question about simplifying a square root of -12. We'll get to that in next. That'll be our next item up for bids. So we saw on our calculator that the square root of -1, I said the square root of -1 is I, right? So I think we could believe that. I think we could buy it. So let's look at example 3 then. Here we go. Example 3. Let's try to simplify. Each of the following. We're going to have number A, the square root of -100. Number B, the square root of -12. Number C, the square root of -675. So remember what happens anytime we simplify a radical and there's a negative under the square root, and there's a negative under the square root, and there's a negative under the square root, we can simply have an I pop out, right? So we're going to have an I pop out in every single one of these. We're going to have an I in our answer for every single one of these. So the square root of -100, well, forget the negative for a second. What's the square root of 100? 10. And an I popped out. So we know there's going to be an I there. We know there's going to be a 10 there. Now we just got to figure out, should we write it I-10? No, we're not in California on the interstate. We're going to write it as 10I, and that's it. That's it. It's just 10I. Now some people might think to themselves, why don't we have a plus or minus? Not because of the negative popping out. Look at the directions. What's the direction say? It says simplify. Are we solving? No. When we're simplifying, unless it says find all the roots, we don't need the plus or minus. Okay. Let's look at number B then. Let's think about simplifying the square root of 12 for a second. When you simplified the square root of 12, didn't you have to find 12's perfect square factor that was bigger than 1? So we would have rewritten the square root of 12 as the square root of 4 times 3, right? Which would have been the square root of 4 times the square root of 3, and the square root of 4 is 2. The square root of 4 is 2, so a 2 pops out. Where's the 2 go? Out front. Why did I write a 2 over here? What's wrong with me? That's supposed to be a 3 over there, right? Okay, so our answer is going to be 2i what? 2i radical 3, and that's it. And that's it. So it's just like what we did before, except an I pops out. True story. Some classmates of mine used to super glue thumbtacks to that teacher's chair. She had a wooden chair, and they super glued thumbtacks to the chair. They were mean to her. They were really mean. I never learned how to handle remainders. We were dividing in our class, and I never knew what to do with remainders for the longest time. So, okay. Number C. Anybody think they figured out number C yet? 5i rad 27. Well, 27's got a 9 in it, so it's not 5i rad 27. We could do better than that. We could do better than that. Let's think about 675 for a second. 675 is 1 times 675. It's 2 times nothing. It's 3 times what? 6 plus 7 is 13, plus 5 is 18. It's divisible by 3. Oh, there. So what's this going to be? 15i rad 3. 15i rad 3. How do we feel about everything up to this point? Pretty decent? Where'd the rad 3 come from? The rad 3 comes from the other factor of the other factor. Okay, well, I did mention that powers of I are cyclical. One of the Common Core content standards is that you'll be able to find any power of I without a calculator. Cyclical? Let's think about the moon. What happens to the moon? It's full. And then it waxes, or maybe it wanes. And then it wanes, and then it's half, and then it waxes. And then it's full. And then it wanes, and then it's half, and then it waxes. Yeah, so a cycle. A repeating cycle that repeats how long? Forever. Forever, ever, and ever, ever? If that happens forever. So let's look at a few powers of I, and let's see if we can't figure out the cycle. I raised to the first power, we said, is the square root of -1, and that's just plain old I. This is the powers of I. Now, if we go to the second phase of the cycle, we could call it the waning phase, or the waxing phase. If we look at I to the squared, is it fair to say that that's the same thing as taking the square root of -1 and squaring it? So what happens when you square a square root? It cancels. So what's this going to leave us with? -1. So I to the squared is equal to -1. Huh. Interesting. Let's go to the next phase of the cycle, the half moon phase. I to the cubed. I to the cubed is going to be I to the squared times I to the first. Now that's -1. I said that's -1 times I. -1 times something is just the opposite of that something. So the opposite of I is -I. Where'd I get -1 from? This -1, let me use some highlighters. This -1 here came from this -1 here. Yeah. I squared is -1, right? Okay. All right. So that's the third phase of the moon. Let's look at the fourth phase. This reminds me of Squidward, because I to the fourth is I squared. No, it's just I love SpongeBob. I to the fourth is I squared. It's I squared. So that's going to be -1, the quantity squared. What's that going to equal? That's going to equal 1. So those are the 4 phases of the I to the power cycle. That's it. If you know those 4, you would know all the other powers of I. You're going to have to be able to find, what example are we on? 5? 4. Example 4, find powers of I. Number A, number B, number C, number D, number E. You're going to have to find I to the 18th. You're going to have to find I to the 417th. You're going to have to find I to the 63rd. You're going to have to find I to the 14th. You're going to have to find I to the 498th power. What? There is no way. Huh? No, but we're going to do them in a second. Yeah. So let's see if we can't look at this cycle business. This is confusing. This is confusing. Hold on a minute. Let's just try to build. Let's try to go a little bit further in the cycle, shall we? Let's see what I to the power 4 is going to, or I'm sorry, I to the power 5 is going to be. I want you to notice where exactly I placed that I to the 5th also. Okay. I to the 5th power, I know we didn't go over our exponent rules, but you should know these from Algebra 1. I to the 5th, is it fair to say that this is I to the 4th times I to the 1st? Does everybody agree to that by the exponent rules? Now what's I to the 4th equal to? 1. And what's I to the 1st equal to? I, and 1 times I is I. I to the 5th is going to equal I. Yeah, does that mean the next one's going to be negative 1? Well, let's find out. Let's find out. I to the 6th power is going to be I to the 4th, again, times I squared. And we said I to the 4th is what? 1. And I squared is negative 1. And so that's going to equal negative 1. So if you know the first 4 powers of I, and you understand the little kicker to it, if you understand the turnaround point, it's a piece of cake. Question. Where are we getting I to the 4th from? We're just using our exponent rules. We're using our exponent rules. These two here add back up to that, right? That's just our exponent rules. Another question. Yeah, and stay with me just for about 55 more seconds and you'll get it, okay? I to the 7th. I to the 7th. That's going to be I to the 4th times I cubed, right? So that's going to be 1 times negative I, or negative I, right? Do you see how that pattern's, it's just doing the same thing over and over again? So what about I to the 8th? I to the 8th is going to equal 1, because it's I to the 4th squared, or 1 squared, or 1. So, wait a minute. Some people get some really big misconceptions about this, and they look for shortcuts, and they look for the wrong one. So, just to make sure that you don't get the wrong shortcut, I'll say this: any even power of I is always real. Is always real. That's going to help you on a multiple choice test question. Any even power of I is always real. So suppose we had something like this: I to the 424th power. And your choices are A, is it I? B, is it negative 1? C, is it negative I? Or D, is it positive 1? Which ones can we eliminate? We can eliminate, well, hold on a minute. Any even power of I is always real. Because of any even power of I is always real, which ones can we eliminate? We can eliminate A, and we can eliminate C, right? So we got it down to a 50% chance of guessing right. All right? So does anybody think they know the turnaround point on this one? There's a catch to this. Everything hinges around one point. Anybody think they know? The last item in the cycle. So here's the point. I to the 4n equals 1. That's what you need to know. Well, what are you talking about 4n? 4n represents multiples of 4. What are you talking about? Well, let's think about multiples of 4. 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, etc. 400, etc. 424 is a multiple of 4, right? You with me? If 424 is a multiple of 4, and I to any multiple of 4 is equal to 1, well, what's our answer to this one? This one's going to be D, right? So here's what you need to know. Here's what you need to know. You need to know I to the first is I. I to the second is, what was I to the second? -1. I to the third is -I, and I to the fourth is... So here's the deal. What happens when you try to find I to the 424th is you see where it falls in the cycle. Okay, here's I to the 4th. Here's I to the 8th. Here's I to the 12th. I to the 16th. I to the 20th. I to the 24th. You're trying to find the nearest multiple of 4 power and then see where relative to the cycle it is. So let me go ahead and grab these. Let's look at 9 in a second. Let me go ahead and cut this out. So the question is, what about I to the 9th? What about I to the 9th? Well, I to the 8th would be here in the cycle, right? Where's I to the 9th going to be in the cycle? It's going back to the beginning. So I to the 9th would equal I. Okay. So let's look at this I to the 18th then. Where's it going to fall in the cycle? Is it going to be here? 16 would be there, right? 17 would be over here. So I to the 18th is going to be -1. What about I to the 417th? Where's that going to go? Well, hold on a minute. What's the nearest multiple of 4 to 417? 416 would put us here. So 417, we start back over. So 417 is going to be 417 is going to be I. What about I to the 63rd? 64 would be here. So it'd be 1 back. So I to the 63rd would be -I. What about I to the 14th? I to the 14th would be -1. I to the 498th. Think about your multiples of 4. Anything that's a multiple of 100 is a multiple of 4, right? I to the 500th would be here, but we're 498. So it'd be -1. -1. How are we feeling about those? Some get it, some are confused. So now that we got that out the way, now it's time to do some operations with I. Example 5. Simplify. 3 minus 8I minus the quantity of -2 minus 4I. I'm going to give you a couple of suggestions here. This couldn't be any easier. I'm not going to lie. This is like 7th grade pre-algebra stuff. All you got to know is the form that you don't want the abbreviation to. What was standard form of a complex number? A plus bi. So that's the format that our answer has to be in. Okay, so if there's an I part, it's got to be second at the end. Also, all that you're going to be doing here is this. This is all there is to it. Simply combine like terms. Like terms. Combine your like terms. 3 is like with -2, right? What's 3 minus -2? Hold on, 3 minus -2. Thank you, it's 5. And then what's -8i minus -4i going to be? -4i, and that's it. That's it. Piece of cake. Really simple. Combine like terms. What do you think? Ready to ramp it up a little bit? Ready or not? Ready or not? Here we go. Example 6. Simplify 4 plus 3i times the quantity 5 minus 7i. Now, you know what's going to happen on the quiz this week? You're going to look at example 5 and you're going to try to do it like example 6. What's the difference between example 5 and 6? Multiplying versus subtracting, right? So on this one, you're actually going to use the FOIL technique. So here we go. Here's your hints that I'm going to give you. Please write down the hints. They are helpful. It's for your good. Still want standard form. So our answer is going to have to be of the form a plus bi. We're also going to use the FOIL method. We're also going to use the fact, use I squared equals -1. And of course, we're going to be combining like terms. Again, combine like terms. Okay? If you do those things, you'll get this answer every time. You ready for this? Let's go ahead and FOIL. What do we get for our first product? 20. Our outer product, minus 28i. Our inner product, plus 15i. And then our last product, minus 21i squared. All right? Doing all right so far? Okay. Well, don't we know that -28i and plus 15i, those are alike, correct? So those combined are going to make minus 13i. Now we got that 20 sitting out front, right? And then we got that minus 21, but wait a minute. What's the one hint say to do? I squared is -1, so we're going to be multiplying that -21 by -1, right? That's going to be plus 21 on the end. So we're going to have 20 minus 13i plus 21. Combine the 21 with the 20. So our final answer is going to be 41 minus 13i. Is that in standard form? You bet. And there it is. That's it. Now, you're ready for the good news. So you all know that the TI Inspire is incapable of manipulating variables, right? Well, that's with X's. The TI Inspire will do these for you if you use the right eye. And when I say the right eye, I mean the correct and proper eye. Not necessarily the one that popped out. One of these days, this calculator is going to load, and I'll show you 4 plus 3i times the quantity 5 minus 7i. But we got to make sure we use the right eye. Got to make sure we use the right eye. tonight you should be able to do approximately at least 3/8 of the Math Excel exercises. One of these days the calculator's about to load. 5 seconds, 4 seconds, 3 seconds, 2 seconds, 1 second. There it is. My computer's having a Monday kind of day. So I'm going to Manila, add calculator. Now what did I say you had to use the right eye? So 4 plus 3i and 5 minus 7i. Here we go. So the quantity 4 plus 3i times the quantity of 5 minus 7i. I didn't use the right eye. I didn't use the right eye. Wouldn't it be nice if there were some button on the calculator that would give me the right eye? It's on the pi button. It's on the pi button, and there's the right eye. There's the right eye. So check this out. Got to make sure you use the pi on the I button, the eye on the pi button. Okay. We ready for this? There it is. You're allowed to use the calculator on Friday's quiz. Friday's quiz will have a component of this on it. And you're allowed to use your notes. It'll do the subtraction one as well. So it's been real, it's been fun. Any shout outs? The basketball team, good luck. Shout out to Calvin Kohler. Shout out to Megan, who's going to watch us again tonight. All right. Have a terrific day. See you all later.
Good.